So picture a person who is just in absolute peak physical shape.
Oh, yeah, like the ideal patient.
Exactly. I mean, we're talking about someone who eats a perfectly calibrated diet, exercises vigorously like 5 days a week.
Mm.
Maybe they even run ultramarathons on the weekends, you
Yeah.
know? So they go to their cardiologist for their annual workup, and their standard lipid panel comes back entirely flawless.
Flawless, low cholesterol, great blood pressure.
Yeah. Their LDL is well below the target threshold. Blood pressure is totally optimal. By literally every conventional metric, they are the absolute picture of cardiovascular health.
Right.
And then entirely out of nowhere, they suffer a massive, life-threatening heart attack.
It's a terrifying scenario, honestly.
It really is. And it's the central paradox driving some of the most urgent conversations in cardiology today. We were doing a deep dive into a fascinating new analysis published in The Conversation that basically completely upends how we evaluate heart disease risk.
It really does. It changes the whole paradigm.
It does. The research points to this hidden microscopic mechanism that just operates entirely under the radar of our standard medical testing. And it affects the biological baseline of millions of people, whether you are a marathon runner or just someone, trying to maintain decent health.
Okay, let's unpack this. We have this glaring clinical blind spot where physically fit individuals are experiencing these catastrophic cardiac events, and the usual suspects, like standard LDL cholesterol, they just don't explain it.
No, they don't. And, well, the problem with those usual suspects is that they have sort of lulled us into a false sense of security.
Right.
When assessing risk, the medical community has spent decades, hyper-focused on low-density lipoprotein. That's standard LDL, the classic bad cholesterol.
The one we all hear about at the doctor's office.
Exactly. But the actual culprit responsible for the paradox you just described is this highly specialized kind of rogue particle called lipoprotein A, or LPA for short.
LPA, yeah. And to understand why it operates as this silent assassin, we really have to look closely at its molecular architecture.
Yeah.
At its core, an LPA particle is essentially just an LDL particle.
So it looks normal at first.
Right. It contains the exact same cholesterol payload, and it has the same structural protein, which is called apolipoprotein B. And that's what allows it to circulate in the blood.
Okay.
Got it. And this is the key. It has a crucial, really dangerous addition.
Okay.
Tethered to that standard LDL particle is an entirely separate, massive glycoprotein called apolipoprotein A.
Yeah, I was reading through the structural breakdown of that apolipoprotein A tail, and it's not just some minor attachment, is it?
No, not at all.
It's this bulky, heavily glycosylated protein that fundamentally alters the physics and the chemistry of the particle. I mean, it transforms a standard cholesterol carrier into a localized wrecking ball.
Wrecking ball is a great way to put it.
The research details how this extra protein drives atherothrombosis, which, means it doesn't just build plaques, it actively causes blood clots too.
Right, it's a double threat.
And it does this through biological mimicry, which is just this brilliant but terrifying evolutionary quirk.
It is incredibly insidious.
Yeah.
What happens is that extra apolipoprotein A tail is structurally homologous to a vital enzyme in your body called plasminogen.
Homologous, meaning it looks almost exactly like it.
Exactly. It's a structural dead ringer. Under normal circumstances, plasminogen is the precursor to plasmin. And plasmin is the chemical your body relies on to dissolve blood clots and just maintain a smooth flow in your bloodstream.
Right.
But because the LPA particle looks so much like plasminogen, it essentially impersonates it. It binds to the exact same receptors on the surface of blood clots and on the inner lining of your arteries.
But because it's just an impersonator, it completely lacks the actual chemical tools to break down the clot, right?
It's totally useless for that.
So it just takes up the parking spaces that the real clot-busting enzymes need. So when your body tries to naturally dissolve a minor clot, the LPT molecules are just, blocking the way, allowing that clot to grow totally unchecked until it eventually occludes the artery and causes a heart attack. If standard LDL is like a regular car causing a bit of traffic in your bloodstream, LPA is like a car covered in double-sided tape. It's going to cause massive pileups, the plaques, and tangle up the traffic flow completely, which are the clots.
That is a perfect analogy. What's fascinating here is how this operates completely independently of the classic warning signs.
Wow.
And how it accelerates the actual physical buildup of the plaque as well. Because beyond the clotting risk, The apolipoprotein tail acts like a molecular sponge for oxidized phospholipids.
Which are bad, right?
Very bad.
Wow.
They are highly reactive, highly inflammatory molecules. So when LPA enters the arterial wall, it literally drags these inflammatory molecules in with it.
Oh, wow. So it's smuggling in the inflammation.
Exactly. And this triggers an aggressive immune response. White blood cells rush in, they ingest the oxidized material, and they transform into what we call foam cells.
Clone cells.
Yeah. These foam cells die and just accumulate, creating this toxic necrotic core inside the artery. So you have a particle that simultaneously accelerates plaque buildup, drives severe localized inflammation, and actively prevents the body from clearing blood clots.
That is just a nightmare combination.
It really is. And because this mechanism is entirely distinct from standard LDL, the danger scales up proportionally with the concentration of LPA in your blood, regardless of how healthy the rest of your lipid profile is.
Which perfectly explains our marathon runner from the beginning.
Exactly.
His regular cholesterol traffic was flowing totally fine, but he had a bloodstream flooded with these inflammatory clot-protecting particles.
Right.
So when a tiny, otherwise manageable plaque ruptured in his artery, his body couldn't clear the resulting clot because the LPA was just blocking the natural breakdown process.
Precisely. The parking spaces were full.
Man, this leads directly to the next hurdle, though. If you have a high concentration of these dangerous particles, the immediate instinct is to ask how to lower them, right?
Of course, that's what any patient would ask.
But the interventions we usually rely on for heart health, cutting saturated fats, increasing cardio, eating a Mediterranean diet, they don't move the needle on LPA at all, do they?
Not even a little bit. The standard lifestyle interventions fail completely because LPA is not a metabolic consequence of your environment or your daily habits.
Right.
It is an autosomal codominant genetic trait.
Okay, so it's all in the genes.
Completely. The levels of LPA circulating in your blood are dictated almost entirely by the LPA gene, which you inherit directly from your parents. This gene determines the specific number of repeating genetic sequences, which we call Kringle-the-Fee type 2 repeats, in your apolipoprotein A.
Kringle repeats, that sounds like a pastry.
I know, it's a funny name for something so serious.
Yeah.
But the biology here is actually somewhat counterintuitive, yet deeply important.
How so?
Well, the more of these Kringle repeats you have in your DNA, the larger the resulting protein is. And surprisingly, the larger the protein, the harder it is for your liver to assemble it and secrete it into your bloodstream.
Wait, really?
Yeah. So people with many repeats actually have very large LPA proteins, but very low levels of it circulating in their blood.
So what does this all mean? If you inherit a gene with very few repeats, your liver churns out smaller LPA proteins, but it does so at an incredibly rapid, efficient rate.
You got it. It floods your system with them. And your genetic baseline is basically locked in early in childhood, and it remains virtually static for the rest of your adult life.
That is just wild.
Yeah, that genetic lock-in is exactly why your marathon runner's strict diet didn't save him. You simply cannot sweat out a genetically hardwired protein secretion rate.
Right. Wait, so I can eat all the kale in the world and run marathons and it won't budge this number? That feels incredibly unfair.
It is frustrating for patients to hear, definitely. There are a few physiological events that can cause very minor fluctuations.
Like what?
For instance, the drop in estrogen during menopause can slightly elevate LPA levels. And certain kidney diseases can impair clearance, causing a buildup. But honestly, these are marginal shifts on top of a fundamentally innate baseline.
Well, this naturally brings up pharmacology then.
Yeah.
Because if lifestyle doesn't work, we usually just turn to medication.
Right? The pill for every ill.
Exactly. And for standard high cholesterol, statins are one of the most successful classes of drugs in medical history. But I was looking at the clinical outcomes for statin therapies applied to high LPA, and the failure rate isn't just disappointing, it's like absolute.
Yes, it's a completely different animal.
In some studies, I read that statins actually cause a slight increase in LPA levels, which is crazy to me. I dug into the pharmacological pathways, and it seems to come down to how the liver actually clears cholesterol.
Right.
Statins work by inhibiting an enzyme called HMG-CoA reductase, right? Which forces the liver to upregulate or just increase the number of LDL receptors on its surface.
Exactly.
And these receptors act kind of like vacuum tubes, pulling standard LDL out of the blood. But LPA doesn't use those vacuum tubes, does it?
No, it manages to evade them almost entirely.
Yeah.
And it's all because of that massive, bulky apolipoprotein, a tail tethered to the particle.
It blocks it.
Yeah, it physically obscures the binding site that would normally allow the LDL receptor to grab hold of it. So the liver is putting out all these extra receptors thanks to the statin, successfully clearing out the regular LDL. But the LPA simply bounces off and remains in circulation.
That's incredible.
The conventional toolbox is just completely mismatched for the mechanics of this specific particle. Even our more advanced injectable medications, the PCSK9 inhibitors.
Right, the really strong ones.
Yeah, those aggressively amplify the liver's ability to clear standard cholesterol, but they only manage to reduce LPA by about 15 to 30%.
Which isn't enough, I assume.
Not if a patient has a severe genetic predisposition. If their LPA is 3 or 4 times the safe limit, a 20% reduction leaves them squarely in the danger zone.
Which means researchers really had to abandon the strategy of trying to clear the particle out of the blood once it's already there.
Exactly. We had to look upstream.
And that brings us to the real breakthrough highlighted in the source material. We are looking at a fundamentally new class of therapeutics called gene silencing.
Yes, this is where it gets really exciting.
Specifically, the use of small interfering RNA, or siRNA. The clinical trial data on this is just staggering. We are talking about sustained reductions in LPA of 80 to 90%.
It's unprecedented.
But the mechanism is what really blew my mind. They aren't treating the blood at all. They are effectively hijacking the liver's internal communication system.
It is a brilliant pivot in molecular biology. To understand siRNA, you really have to look at how proteins are manufactured in the first place.
Okay.
Inside the nucleus of your liver cells, your DNA holds the master blueprint for the apolipoprotein A. But the DNA never leaves the nucleus.
Well, it's too important to leave.
Exactly. Instead, it creates a temporary copy called messenger RNA, or mRNA. And that copy carries the instructions out to the cellular machinery that actually builds the protein.
Okay, I follow you.
So these small interfering RNA therapies, they are engineered to perfectly match the specific sequence of that LPA messenger RNA.
So instead of trying to clean up the sticky cars off the highway with statins, gene silencing is basically like calling the liver's manufacturing plant and completely canceling the production order.
Exactly. You are intercepting the message before the factory even gears up.
It's literally like intercepting the mail carrier who is delivering the blueprints to the factory floor.
Yes, perfect way to think of it.
The siRNA drug is injected, and what's fascinating is how they ensure it only goes to the liver. Because that was a big hurdle,
A
right?
huge hurdle. You don't want this drug going into every cell in the body.
Right. So they attach a specific sugar molecule, a GalNAc ligand, to the RNA strand. And the liver cells have receptors specifically looking for this exact sugar, so they just pull the drug right inside.
It's a Trojan horse, basically.
Yeah. Once inside, the siRNA binds to a structure called the RNA-induced silencing complex, or RISC. And this complex uses the drug as a targeting guide to hunt down the messenger RNA carrying the LPA instructions. And it physically cleaves the mRNA right in half.
It just destroys it.
Yeah, the message is destroyed before the cell can even read it.
If we connect this to the bigger picture, it represents a massive paradigm shift in treating hereditary cardiovascular disease.
I mean, it sounds like sci-fi.
It does, but it's happening. By destroying the mRNA transcript, the liver never manufactures the apolipoprotein a tail. The assembly line simply halts.
Wow.
And without that tail, the sticky, inflammatory, clot-protecting particle is never formed in the first place. We are moving away from the sort of blunt force pharmacology of trying to sweep up dangerous proteins in the bloodstream and moving toward precision upstream inhibition.
That's amazing.
The trials currently underway, which are evaluating drugs like pelacarsen and olpasiran, they are showing that a single injection can keep the gene silenced and LPA levels suppressed by over 80% for months at a time.
Months at a time, from one shot.
Yes, it's truly revolutionary.
Well, the science is incredible, but the reality is that these Phase 3 clinical trials are still ongoing. These gene silencing therapies aren't something a patient can just, ask their local pharmacist for today.
No, not yet.
The timeline for broad commercial approval could still be a few years away. So what can you, the person listening to this deep dive right now, actually do today to protect yourself?
It's the million-dollar question.
Because right now, the biggest threat seems to be the lack of awareness. I mean, LPA is entirely absent from the standard lipid panel. When a physician runs a routine blood test, they measure total cholesterol, HDL, LDL, and triglycerides. The LPA concentration is a complete blind spot unless specifically requested, right?
It is, and that blind spot is really just a relic of medical pragmatism.
What do you mean?
Well, For decades, the prevailing logic in primary care was, why routinely screen for a genetic marker that we have no specific highly effective treatment for?
Ah, right. If you can't fix it, why test for it?
Exactly. It was viewed as actionable only in really specialized lipid clinics. But as the epidemiological data has cemented just how dangerous LPA is, and as these gene therapies inch closer to reality, the international guidelines have shifted dramatically.
Okay, that's good news.
Yeah. Organizations like the European Atherosclerosis Society now actually recommend that every adult get tested for LPA at least once in their lifetime.
Just once.
Just once. Because the level is genetically fixed, it isn't something that needs to be tracked annually. One specific blood test gives you your lifelong baseline.
Okay. Here's where it gets really interesting, though. Let's say I take this advice. I go to my doctor, I specifically request the LPA assay, and the results come back alarmingly high.
Okay?
I have this piece of paper telling me I have a severe genetic risk for atherothrombosis, but I can't easily change it yet because those Suriname drugs aren't on the market. Isn't that just depressing information to have?
I hear that a lot.
I mean, I'd be walking around knowing my arteries are accumulating this inflammatory plaque, and I feel powerless to stop it. How does the medical community expect patients to handle that kind of information?
The psychological burden is a very real factor, and it's something preventative cardiologists are actively navigating right now. But honestly, the alternative, remaining in the dark and experiencing a sudden cardiac event like our marathon runner, that is far worse.
Yeah, fair enough. Ignorance isn't bliss here.
Exactly. We really have to reframe how we view the test result. A high LP reading shouldn't be viewed as a definitive death sentence. It should be viewed as a vital global risk indicator.
A global risk indicator, meaning what exactly?
It tells you precisely how to calibrate the rest of your health strategy. It tells you exactly how little margin of error you have with your other lifestyle choices.
Oh, I see. It redefines your margin of error.
Right.
If you know you have this unchangeable structural weakness in your cardiovascular system, you literally cannot afford to be relaxed about the factors that are under your control.
Exactly. You had to tighten up everything else.
So if a normal patient's target for standard LDL or apolipoprotein B is, say, 100 milligrams per deciliter, someone with high LPA might need to be pushed down to 50 or even 30 milligrams per deciliter using statins and those PCSK9 inhibitors we talked about.
Yes. You aggressively strip away the standard plaque-building materials just to give your arteries maximum breathing room.
That makes total sense.
That is the exact clinical strategy. You cannot eliminate the LPA yet, so you just dramatically reduce the overall burden on the arterial walls.
Right.
You maintain pristine blood pressure to prevent micro tears in the vascular lining where LPA really likes to accumulate. You strictly manage blood glucose to prevent endothelial dysfunction.
And obviously smoking is out.
Entirely off the table. It multiplies the oxidative stress and the whole inflammatory cascade that LPA thrives on. So identifying this genetic risk marker isn't about inducing despair. It's about mobilizing an aggressive, highly targeted defense across every other biological front.
You are actively buying your blood vessels time and health while the next generation of targeted molecular therapies clears the final hurdles of clinical testing.
Exactly. You are holding the line.
So the immediate takeaway is clear: do not stay in the dark. We've traced the path of a really profound medical mystery today.
We covered a lot of ground.
We did. We started with the paradox of the perfectly healthy athlete suffering a sudden heart attack, which forced us to look past standard cholesterol. We examined the sophisticated, frankly insidious biology of lipoprotein, how its lipoprotein tail mimics clot-busting enzymes, drives inflammation, and just entirely evades the LDL receptors that statins rely on.
Right.
We confronted the reality that this risk is genetically hardwired and impervious to kale salads and long runs. But we also explored the phenomenal mechanics of Suriname gene silencing, intercepting the liver's messenger RNA to halt the production of this molecule right at the source.
That's a true game changer.
And most importantly, we mapped out a strategy for the present. Getting that one-time blood test to understand your baseline and aggressively managing your broader cardiovascular risk.
This raises an important question as we look toward the horizon of cardiovascular medicine.
What's that?
Well, the source literature emphasizes that LPA levels are determined at birth, right? And they remain essentially stable for life.
Right, locked in.
We are currently testing gene silencing on adults who have already accumulated decades of arterial damage. But if these therapies prove to be as safe and effective over the long term as the early data suggests, we are looking at a radical shift in preventative care.
Oh, I see where you're going with this.
Could we see a future where we screen teenagers or even young children for this specific genetic marker?
Wow.
If they carry the high-risk gene, could we intervene with targeted RNA therapies to just turn off the production of LPA before a single inflammatory cell ever attaches to their arterial walls?
We are talking about intercepting hereditary heart disease before it even has a chance to begin.
Exactly. Wiping the slate clean early.
It's a remarkable glimpse into a future where your genetic destiny is basically no longer an absolute sentence, but merely a diagnostic starting point.
Right. A starting suggestion, really.
A future where that highly fit marathon runner can keep hitting the pavement with absolute confidence in their cardiovascular health.
That's the dream.
It is. Thank you so much for joining us on this deep dive into the hidden mechanisms of heart health. Keep staying curious, make sure to ask your doctor about your own lipid panel, and we will catch you next time.